Hi everybody, my name is Vishesh and welcome to yet another ABAQUS tutorial in the Advanced Design of Modern Aerospace Structures series. Today we're going to simulate the failure of a ductile epoxy adhesive. This is a two-part question, so we're going to go through part one in this video. The problem statement is so. We wish to model the failure of a ductile epoxy adhesive which bonds two substrates made of a heat-treated steel. And what we need to do is determine the mode 1 critical energy release rate using VCCT in ABAQUS. We've been given the geometry and the materials of all of our constituent parts. We also know the thickness of the adhesive layer. We are able to calculate the Young's modulus of the adhesive, which is 1363.6 megapascals. And we can also calculate using the cantilever beam formula the expected deflection, which is about 0.07 millimeters. From the graph that we've been given, we can make out that around 1400 newtons is what our failure mode is what our failure load for the adhesive is. And so 1400 newtons is the load that we're going to apply on our double cantilever beam for this video. Let's go to ABAQUS now. Welcome back to ABAQUS. We're going to start by creating our model database with a standard explicit model as usual. I'm also going to save my file. I'm going to call it ECB1. All right. So as usual, we start by creating a part. It's a 2D part, type deformable with a shell-based feature. My approximate size is going to be 1 because we're using SI units here. I'm going to press continue and I'm going to wait for the Cartesian plane to pop up. And once it does, we're going to start creating a rectangle that's going to be the same shape as my cantilever. So my top right corner of the cantilever is at 0.29 and 0.0127. So that's the structure of my cantilever, but I know that the force that I am applying is not at the edge of the cantilever itself, but at 12.7 mm. So for that, I need a node over here that I can uh, apply a concentrated force to. So for that, I'm going to create section first. So again, it's going to be 12.7 mm from the edge. And I go to create wire, add wire, and simply draw a line between these two nodes and press done. And as I press OK, you'll see another section on my part. Now that's my cantilever. We know that our geometry has three parts, right? So two cantilevers and an adhesive layer. The two cantilevers are identical, so we're going to create just the one part for them. But for the adhesive layer, we do need to create another part. Same properties, different geometry. So my adhesive layer is shorter than my cantilever layer, than my cantilever itself. So I'm gonna give it the exact size that we know from the geometry. So 0.2 mm thickness, that's my adhesive layer. I click done and we're done with creating our parts. Our next step is the property module where we want to define two materials. The first is steel. As you know, I do like to define the density, so I'm going to define the density for this one too. But what is most important is the mechanical properties. So that's 200 GPa and Poisson ratio of 0.3. Oops, Poisson ratio of 0.3. I'm going to double check that my Young's modulus is correct. It is. Next, I want to create my adhesive layer. I know only the mechanical properties of the adhesive, so I'm going to give it the Young's modulus that we calculated and also the Poisson ratio that we know. All right, so our material properties have been defined. Next, we define two sections. First one I'm going to call steel. It's a homogeneous solid, of course. The material will be steel, and I'll also give it the breadth of the cantilever that we've been given, the breadth of the entire structure that we've been given, which is 25 mm. And similarly, I'm going to define a section that is called adhesive, and I'm going to assign the right material to it as well as the right thickness. Next, we need to assign these sections to our parts. So I click on Assign Section. I have my adhesive layer up, so I'm going to assign the adhesive section to the adhesive layer first and click OK. And do the same thing with my cantilever as well. All right. Next, we move to assembling our geometry. I'm going to create an instance over here, and we're going to be creating these instances and assembling them in a way that's different from what we've done before. So I'm first going to select both of these parts uh, by pressing the Shift button on my keyboard. I'm going to make them independent. I'm also going to offset them because I want to join them later. I apply this first. Next, I click on part 1 again because I need the second cantilever, and I press OK. Next, I click on Translate Instance. The instance I want to translate first is my adhesive layer, and I press Done. And what I do is I select the top right corner or the top right node of the adhesive layer, and I translate it to the bottom right node of my upper cantilever, and I press OK. Next, I click on my second cantilever to translate it. I click on the top right node of my second cantilever and connect it to the bottom right node of my adhesive. And there you go. Our geometry is ready. I'm going to save this. We move on to step. We know how to define a step. I'm going to click on Static General and press Continue and toggle on large geometric deformations because there's going to be large geometric deformations when we apply a force on a cantilever. I pressed OK. I'm also going to define a new step output, and that output is going to be in the failure fracture section, and it's called ENRRT. This is the energy release rate, and this is essentially the energy release rate that's been asked of you in this question. So I'm going to at least have ENRRT, but just for information, I'm going to have a bunch of other outputs as well, the bond states, the time at bond failure, the release rate ratio, and so forth. I'm going to press OK. So what we're going to do now is the most important step of this simulation by far, which is the interaction module. But before I do anything in the interaction module, I'm going to define a few surfaces and a couple of sets, right? So for the first thing I'm going to do for that is I have Shift held down, and I'm going to select my cantilevers and isolate my adhesive layer by clicking on Remove Selected so that I have just my adhesive layer over here. Next, I go to Tools, Set, Manager, and what I want to do here, I'm going to delete this. What I want to do here is create two sets. One of the top of the two nodes of the top surface of the adhesive layer and one of the two nodes on the bottom surface of the adhesive layer. So I'm going to click Create here, call this ADH top. Click on continue. And I'm going to select node 1 on the top and node 2 on the top. And I'm going to press done. Similarly, I'm going to create ADH bottom. I'm going to select node 1 on the bottom and node 2 on the bottom and press done. Just take care that no edges are selected. I'm going to dismiss this now. Next, I need to create four surfaces. Bottom surface of the top cantilever, the top surface of the bottom cantilever, and the two surfaces of the adhesive. Since I already have the adhesive layer up, I'm going to select on Tools, Surface Manager, click Create. The first one I'm going to call Adhesive Top. What I'm going to do is select the top edge of the adhesive and press Done. Similarly, I shall create adhesive bottom. I'm going to select the bottom edge of the adhesive and press Done. Next, I'm going to pull both of my cantilevers back up by clicking on Replace All. So I have my cantilevers back up. I'm going to click Create, Top Cantilever, press Continue, and select the bottom surface of the top cantilever. It's done. Similarly, I shall do bottom cantilever, continue, select the top surface of the bottom cantilever and press Done. Now that all those definitions are done, what I'm going to do is define an interaction property, right? I'm going to call this VCCT criterion, press continue. This is essentially the property that defines the failure of the adhesive, right? So it's going to be a fracture criterion. Mode 1 critical energy release rate is what we've been asked in the first part of the question, right? So what I'm going to do is, since I do not want my crack to propagate, I just need the highest value of the critical energy release rate for this configuration. I'm going to give this an abnormally high critical energy release rate, exponent is 1, so that essentially the cantilever doesn't fail or the adhesive layer doesn't fail, but it does give me the actual maximum value of the critical energy release rate for that interaction, right? The other properties remain the same and I press OK. Next, I define the first interaction, the top surface interaction. It's a surface to surface contact. I press continue. It asks me to manually select the main surface, but since I have the surfaces defined, I'm going to click on surfaces over here. And my main surface is going to be my top cantilever. And I press continue. My secondary surface type is also a surface, and that is the top layer of the adhesive. And I press continue again. My sliding formulation for a surface to surface contact has to necessarily be small sliding. And here's where we find out why I define those two sets. I'm going to go to bonding and I'm going to limit bonding to those secondary nodes only. For ADH, for the top interaction, it's ADH top. And I'm going to click OK. I'm going to do the exact same thing now for the bottom interaction. So bottom cantilever, surface, bottom adhesive, small sliding, and limited to ADH bottom. My interaction property, of course, is VCCT, and I press OK. So now that that's done, another new step for this module is called track management. So I open a track manager. I define a track in my adhesive layer or in my two interactions is what I do. So I click create here, track 1, debond using VCCT and continue. My step, I have just one initiation step and my first contact pair interaction is stop. And similarly, I define another contact for the bottom. There. Dismiss. Now that the hard part's done, we move on to load. For load, I first need to encaster the end of my cantilever or my DCB. So this is my first boundary condition. I prefer to select these individually by myself. So I have shift held down and I'm going to select these three edges and press down. And my type of boundary condition, of course, is going to be encaster. Next, I define my two loads. So load one out here is, as we discussed earlier, 1400, which is the failure load, and another 1400 load at the same location on bottom cantilever. All right, loads have been defined. Finally, we mesh. I click on seed part instance, select the entire cantilever, and give it a rather simple mesh of 1 mm element size and press OK. Next, I ask it to mesh part instance, select all of them again, and press done. I also want to change my element type because the default element type is CPS4R, but I do need incompatible mode, so I'm going to go with CPS4I and press OK. Now that we've set up our simulation, we just need to submit the job. I'm going to go to Job Manager, click Create Job 1, Continue, and submit the job. Of course, as per usual, you're free to monitor the job. Uh, it should be done in not more than a few seconds, and we should ideally have our results pretty soon. We might get a few warnings. That's mostly to do with uh, our bonding criterion as well as our uh, output field outputs, right? But our analysis is done. I click on dismiss and I want to look at the results, right? So of course, by default, the results that we're going to be shown are the stress values. We can also have a look at the deformation values, and you'll find that at the location where the force has been applied, it is actually very close to uh, the value that you get through the simple cantilever beam formula, which is PL cubed by 3EI. What we're interested is the maximum uh, strain energy rate, right? Which is our ENRRT1. And the strain energy rate maximum that we get is 22.2. And I expect that to be the same for both of them. So 22.2. Now that is the result that we needed in this part of the analysis, right? We're going to use this 22.2 as our strain energy rate when we define the VCCT criterion for the next geometry that we're going to create in the next video. So see you there.